Welcome back to the Deep Dive. Today, we're getting into the nitty-gritty of how things were actually put together.
Yeah.
The stuff you don't always see, like the engineering behind bridges, planes, all the complex machines out there.
Yeah.
It all comes down to things like, well, precision, the right materials, safety. Okay, so let's jump right in with something maybe a bit counterintuitive. Why would you heat metal before you even start the actual welding? It feels like adding an extra step. What's going on there? What are we trying to avoid?
That's a great question. It really gets to the heart of managing stress within the metal itself. For some materials, particularly things like carbon steels, especially when you're using manual metal arc, well, stick welding, preheating is often a really critical step, the main reason, to stop something called parent metal cracking.
Parent metal cracking.
Yeah.
So not a crack in the weld itself, but in the original metal pieces being joined. That sounds quite serious. How does warming it up first stop that?
It's all about managing the thermal shock, essentially. Picture this. You've got a thick piece of relatively cool steel, right? And then bam, this super intense focused heat from the welding arc hits it. That spot gets incredibly hot instantly, while the metal just next to it is still much cooler.
Okay, huge temperature difference in a tiny area.
Exactly, a really steep gradient. And as that little pool of molten weld metal cools down and cools down fast, that difference creates massive internal stresses in the surrounding parent metal. It's like trying to stretch just one tiny part of something rigid. Something's got to give, right? Preheating brings the overall temperature of the base metal up, so that difference, that gradient, isn't nearly as extreme.
Right, it smooths out the temperature change.
Precisely. It lets the weld zone and the area around it cool down more slowly, more uniformly. Think of it like a warm-up, metabolically speaking. It gives the material a chance to adjust, to distribute those stresses without cracking. We sometimes call the cracks it prevents cold cracking because it happens as it cools. Without preheat, you could have a weld that looks perfect on top but has hidden cracks underneath. Really dangerous.
That makes a lot of sense. Slowing down that cooling, managing the stress.
Yeah.
Okay, let's switch gears a bit. Another term you hear is hydrogen control in welding. Hydrogen, like the gas. What's it doing in a weld, and how can a welder control it just by picking, say, a different welding rod or stick?
Yeah, hydrogen. It's another one of those invisible troublemakers. Controlling it is really vital, especially with high-strength steels, or anywhere that hydrogen-induced cracking just isn't acceptable. So when the job specs call for hydrogen control specifically for manual metal arc welding, the choice of electrode, the stick, is absolutely key, the usual choice. It's what we call a basic electrode.
A basic electrode. So the electrode itself is the solution. How does that work? What makes it basic and good at fighting hydrogen?
It's all down to the chemistry of that coating on the electrode, the flux. Basic electrodes are made with, well, very, very low levels of hydrogen baked into that flux coating from the start. See, when the arc burns, any moisture from the air, maybe even tiny amounts in the coating itself, can break down and release hydrogen atoms. Those atoms can dissolve into the molten weld pool.
Okay, so hydrogen gets into the liquid metal.
Right. And if it gets trapped there as the metal solidifies and cools down, it can cause major problems. Things like hydrogen embrittlement or delayed cracking, nasty stuff that might not even show up for hours or days. Basic electrodes just introduce far less hydrogen to begin with because of their coating. Plus, the slag that forms from that basic flux is designed to actually help any stray hydrogen diffuse out of the weld as it cools, like opening a tiny window for it.
So it minimizes what goes in and helps what does get in to escape.
Exactly. It drastically cuts the risk of those delayed hydrogen-related problems, which is crucial for weld quality and reliability. It shows how much engineering goes into even just the coating on a welding rod.
That's fascinating. It really does highlight the unseen details. Okay, speaking of the materials, the filler wire itself, here's something I've wondered. Could you, say, take a standard stick welding electrode, scrape all the flux coating off, and then just use that bare wire as filler for a different process, like TIG welding? It feels wrong, but why?
You're right to feel it's wrong. Yeah, as an inspector, seeing that would be an immediate red flag. You'd have to object. The absolute core reason. The metal composition of that wire is probably totally wrong for TIG welding that material.
So it's not just that it's bare wire versus coated wire, it's the actual recipe of the metal, the atoms inside.
Spot on. It's metallurgy down to the element level. Different welding processes, different base metals, they all need very specific filler metal chemistry. The wire inside a stick electrode is designed to work with its flux. The flux does things like adding alloys, maybe compensating for elements burned off in the MMA arc. It's formulated to give you the right strength or toughness or corrosion resistance in that specific process. Strip the flux off and you've just got a wire. But its chemistry is tailored for MMA, not TIG.
Okay, I see. So using it in TIG could lead to, bad welds.
Oh, definitely. You could get welds that are brittle, prone to cracking, full of pores. Maybe they just don't bond properly with the parent metal. It's not about saving money on wire. It's about fundamental compatibility. Using the wrong filler chemistry is just asking for failure. You can't mix and match like that.
Right. Precision down to the chemical level. That's a key takeaway. Now, shifting slightly, material properties. Magnetism. We think of metals as magnetic generally, but are they all? Is there a common type of metal alloy that actually isn't magnetic?
That's a common misconception, yeah. Lots of metals are magnetic, but definitely not all alloys. A really common, widely used example of one that's not magnetic is austenitic stainless steel.
Austenitic stainless steel.
Yeah.
Like the kind used in kitchen sinks and cookware sometimes, that stuff. So unlike regular steel, it wouldn't stick to a fridge magnet. That's surprising for a lot of people, I bet.
That's exactly right. Compare it to something like a 4% chrome moly steel you might find in pressure equipment, or a 12% chromium steel used for tools. Those are definitely magnetic. It's down to their crystal structure. Austenitic stainless steel has a particular atomic arrangement, face-centered cubic, if you want the term, that just doesn't allow it to become magnetized easily. And this non-magnetic property isn't just a curiosity, it's often incredibly important.
How so? Where would that matter?
Well, think about medical devices, especially anything used near MRI machines. Magnetic materials are a huge problem there. Or really sensitive electronic gear, scientific instruments, maybe even some parts in nuclear facilities where stray magnetic fields are a no-go. So its non-magnetic nature makes it essential for a whole range of high-tech or safety-critical uses.
That's a great example. A seemingly simple property with massive implications. Okay, let's turn now to something that's absolutely top priority. Safety. Imagine you're inspecting a job site. Arc welding is happening. And you notice the fittings they're about to weld are, cadmium plated. What's the immediate reaction? The non-negotiable step.
Oh, that's one of the nightmare scenarios. There's only one possible action. Zero hesitation. You stop the operation at once. Immediately. Full shot.
Stop everything. Right there. Why such an immediate, drastic response? What's the specific danger with cadmium plating?
Because heating cadmium, welding it, grinding it, even just getting it hot releases fumes that are incredibly toxic, extremely poisonous. Breathing those fumes, even a little bit, can cause, catastrophic health damage, severe lung injury, kidney failure. It can damage your bones long-term. It causes something called cadmium poisoning, and it can kill quickly. The risk is so high, so severe, that there's no safe way to do it. No amount of ventilation, no mask, nothing makes it okay.
Wow. So it's not a risk you manage, it's a risk you absolutely must avoid entirely.
Precisely. It's an immediate hazard to life. Human safety overrides everything else: production, cost, schedule, everything. Identifying that hazard and stopping the work instantly. That's one of the most critical duties an inspector has, no question about it.
That really underscores the stakes involved. Okay, we've covered some really fascinating ground today, from, preheating to stop those hidden cracks, to picking the right electrode to fight off hydrogen, understanding why the filler wire's chemistry is so critical, and even appreciating why some metals, like austenitic stainless, aren't magnetic. And ending on that crucial safety point about cadmium, it feels like knowing these specifics really does give you a clearer picture of what quality and safety look like in fabrication.
Absolutely. And each point, though specific, connects to bigger themes, doesn't it? It's all about precision, understanding the materials you're working with, and being incredibly diligent, especially about safety. It shows how seemingly small details, the temperature before welding, the coating on a rod, the plating on a fitting, can have huge consequences for strength, lifespan, and fundamentally, people's safety.
So maybe a final thought for everyone listening, whether you're involved in this field or just curious about the world. The next time you see a bridge, a building, any complex piece of machinery, maybe just pause for a second. Think about those unseen choices we discussed, the materials picked, the processes used. How might those hidden decisions be affecting everything from its basic strength to its long-term safety and reliability? Thanks for joining us for this deep dive.